All right, students, welcome to the third and final video for topic 7.2, nuclear reactions. In this video, I'm going to talk about nuclear fission and nuclear fusion. We will talk more about these later when we do the higher level nuclear physics. So for now, I'm going to talk about what you need to know as core, a standard level core and higher level core, okay? Now remember, when a decay or a reaction takes place, as we discussed in the last video, the mass of the decaying nucleus is greater than the combined masses of the products, which means that the binding energy of the product nuclei is greater than the binding energy of the decaying nucleus because some energy is converted to kinetic energy after the reaction, as we discussed in the last video. Now, this term nuclear reaction is very different, for example, than like a radioactive decay. It's a very, very different situation. Nuclear reaction refers to when two nuclei collide to produce one or more particles that are different than the original ones. This is also called a transmutation, okay? And it's different from radioactive decay because it takes place because of a collision, all right? So it's an induced change in a nuclide. It's a disintegration of a stable nucleus by striking it with another nucleus that has energy, an atomic or subatomic particle, photon, or a gamma ray. So in principle, a nuclear reaction could involve three or more particles colliding, but this is rare, especially when you think about how difficult it would be to get three or more particles to hit the same thing, okay? Now, nuclear reactions produce a lot of energy. And there are natural nuclear reactions that happen often in nature, cosmic rays from space, fusion inside stars, etc. We'll talk more about fusion, nuclear fusion inside of stars when we talk about astrophysics, okay? Now, artificial nuclear reactions are employed to produce useful energy, okay? And that energy can be used for sort of peaceful means, like energy for use in modern society, or weapons, all right? Now, it was Rutherford's experiment, nitrogen to oxygen experiment, was one of the first artificial nuclear reactions ever observed, okay? And in this case, we had an alpha particle that came in and it hit a nitrogen atom, excuse me, knocking out a proton and creating an oxygen atom, okay? And we found in this particular case, we did this example last time in the last video, we found that the mass defect, or delta M, to be 0.001833 atomic mass units, okay? Now, in Rutherford's experiment, the alpha particle came in having a kinetic energy of 1.707 mega electron volts to make up this difference, okay? Now, generally, in a reaction, we say if A plus B goes to C plus D, then energy is released if delta M is positive, right? I mean, we also said that delta E equals delta MC squared, and it's negative. If it's negative, then the decay will not occur because there's not enough energy to make that decay occur unless some more energy is provided, all right? Now, if we consider a uranium-235 nucleus that absorbs a neutron, it's hit by a neutron, okay? And so if it absorbs that neutron, it's going to become a 236 uranium nucleus. Now, the 236 uranium nucleus is unstable, and it will immediately decay, it turns out, into 5 particles, okay? Barium, krypton, and three other neutrons, okay? So note that the 236 nucleus is split into smaller pieces, lighter nuclei, and the multiple neutrons are products, okay? So these are key characteristics of nuclear fission, okay? And nuclear fission, therefore, is defined as a reaction in which a nucleus splits into lighter nuclei after being hit. And usually it's being hit in fission with neutrons. It produces neutrons and often photons or gamma rays, okay? So the take-home message for you here is that nuclear fission involves heavier nuclei as the products and lighter nuclei, or sorry, heavier nuclei as the reactants and lighter nuclei as the products, okay? All right, so what exactly happens? Okay, well, you have a neutron that hits a target nuclei with an atomic mass number, A0. That neutron is captured by the nucleus, and what happens is then a new element is created because that atomic mass number changes, and of course that's what determines what an atom is on the periodic table. Now, the resulting unstable nucleus that will then spontaneously split into lighter nuclei, and that's going to release energy in the process, okay? So the uranium-235 captures the neutron as we saw before, creating an unstable compound nucleus is the term, uranium-236, and the uranium-236 splits into two daughter nuclei, okay, the Kr92 and the Ba141, 3 free neutrons, and a gamma ray, which is not shown, okay, and that's all shown in this diagram right here, okay. Now, if more U-235 atoms are around, their nuclei could be hit by one of those 3 neutrons created by this reaction, okay? These are what are called fission products, and if those nuclei are hit by those neutrons, then the reaction could then keep going. Those other 235 nuclei atoms could then be converted into uranium-236, okay? And this is one of many possible reactions when uranium-235 fissions. It's not the only one, okay? Okay, so here's a case where you have lots of uranium-235 atoms, and you see that each of those reactions involves 3 neutrons, which can then hit the nuclei of other uranium-235 atoms, shown here in this GIF up top. Now, if there's enough uranium-235 around, the product neutrons will collide with other 235 nuclei. It's only about 1 in 3, and this is what's called a chain reaction. There's some other important things you need to know about fission. The first one being that it was discovered in 1938. The second one being it's an exothermic reaction, if you remember from your basic chemistry. This means that energy is released, okay? And it's released both as electromagnetic radiation or gamma rays and as kinetic energy of the fragments. So what it does is it heats the bulk material where fission takes place. In fact, keeping the fissionable material cool is a major safety consideration of nuclear power plants, and we'll talk about that later, okay? So substances called nuclear fuels undergo fission when they're struck by fission neutrons, and in turn those emit neutrons when they break apart, so a self-sustaining nuclear reaction takes place. It's also, because there's so much energy created by fission, and we'll talk about actually the amount of energy that's created, it can be used in a nuclear weapon situation, right? And you should know that the term nuclear bomb is the same as the atomic bomb. Both of them are referred to the same physics that's happening in an uncontrolled nuclear reaction, okay, where you want all that energy released all at once in an uncontrolled situation to inflict the most damage possible, okay? Now, a certain amount of the original 235 must be present for chain reactions to continue effectively. This is called the critical mass, okay? So in order for fission to produce energy, the total binding energy of Kr92 and Ba141, of course, must be higher than that of uranium-235, as we discussed in the previous video, okay? And this is indeed the case, all right? If you look at the binding energy curve, you see that indeed this is the case, all right? So zooming in on this part of the binding energy curve, you see that Kr92 and Ba141 are higher than uranium-235, okay? Let's see, where are they here? Kr92, it's going to be somewhere in here, and then Ba141 is right in here, okay? All right, so you see that that's indeed the case. The higher binding, meaning it's higher on the y-axis in our binding energy curve, okay? Now, exactly how much energy is released in this reaction, okay? Before we have this discussion, you guys have studied hopefully isotopes in chemistry, and in different isotopes of the same element are just different versions of it that have different numbers of neutrons in the nucleus, but of course retaining the same number of protons, or they wouldn't be the same element. Okay, so the isotope U-235 is often used because it turns out that U-235 readily absorbs a thermal neutron. Okay, a neutron having a particular energy. Okay. Pu-239 is also sometimes used, okay? And the equations look like this, right? You see this equation here, okay? This is the first one, so the neutron comes in, collides with the uranium-235 nucleus, okay? Here's the 236 nucleus, which then spontaneously decays into 3 neutrons, okay? All right. Now, if I consider the atomic masses, or the atomic mass units, here of the products and the reactants, okay, and I look at the mass defect, or I'm going to eventually come up with the mass defect, right? The mass of the reactants, I get 236.05257 atomic mass units. The masses of the products, okay, the difference I find is 0.18583 atomic mass units. So then, of course, the energy release, which is now a very familiar equation, a very familiar calculation for you, is 173.1 mega electron volts. That's per nucleus, okay? So 1 kilogram of uranium-235 could release about 10 to the 14 joules. That's an incredible amount of energy for 1 kilogram of a substance, okay? Now, another way to think about the reaction is that the binding energy per nucleus of uranium-235 is about 7.6 mega electron volts. If we assume that the nucleus fissions into 2 fragments, and each of them has 120 nucleons, okay? Each of these has a binding energy per nucleon of about 8.5 mega electron volts. Therefore, the energy released when uranium-235 fissions would be the difference between them, which is about 0.9 mega electron volts per nucleon. That's huge because there are 235 nucleons involved in each fission process. So the total amount of energy released would be that number times 235. That's 212 mega electron volts per nucleus. So we're talking about incredible amounts of energy, okay? Now, fission, it turns out that fission is the only commercial nuclear energy source, okay? Fusion is not used as a commercial energy source, which we'll talk about in just a little bit why that is. About 6% of the world's energy and about 13 to 14% of the world's electricity is uses nuclear fission as its source. But of course, there are major environmental consequences. So the fission products are themselves radioactive, and they're not reusable. So a big question facing sort of your generation and subsequent generations is how do we get rid of spent nuclear fuel, which is still radioactive? Now, nuclear energy is a very clean energy source in terms of not producing, not adding carbon dioxide to the atmosphere and so forth. But there's an issue of all these fission products that are radioactive, and what do we do with them? Well, in some cases, governments have buried them. There's been talk of putting them under the ocean in ocean trenches and things like this, but it's a major problem. Okay. The next kind of nuclear reaction we're going to talk about is nuclear fusion, and this is a reaction in which 2 or more lighter atomic nuclei collide at high speeds to create a new heavier type of nucleus, okay? So this is just the reverse of nuclear fission, which was heavier into lighter. So an example of this is deuterium and a tritium collision. In this particular case, matter is not conserved because some matter of the fusing nuclei is converted to photons or energy. Okay, so you need to keep that in mind with fusion. It also creates photons as nuclear fission did in that case. Okay, so if you remember, fission involves splitting a massive nucleus on the far right of the binding energy diagram, like uranium-235, into less massive fragments with higher binding energies. Okay, fusion just does just the opposite. It involves moving from the far left to the right towards the center, and fission involves moving from the far right to the left towards the center. Okay, so with fusion, 2 nuclei with relatively low masses and low binding energies are actually fused together to form one with a much higher binding energy. So it's quite different than fission. Okay. All right. So again, what exactly happens? Well, in order to fuse these two particles together, these 2 atoms together, you have to heat it to very, very high temperatures. So the particles have to acquire very, very high amounts of kinetic energy, so that the nuclei get really, really, really close together. They get so close together that the strong nuclear force pulls them together. So they have to get together. They have to get close enough, on the order of 10 to the minus 15 meters, which is about the average radius or diameter of an atomic nucleus, okay? So it has to overcome electrostatic repulsion where the strong nuclear force takes over. Turns out that temperatures on the order of, 10 to the 8th degrees Celsius are needed, okay? This is called the thermonuclear reaction. So the energy release is greater than the energy put in to heat the material because of the increased binding energy of the products, okay? Now, fusion doesn't harm the environment because there's no radioactive byproducts or waste. And fusion occurs naturally inside of all stars, okay? Now, fusion is not used as an energy source, and the reason is because the energy required to heat the material is enormous, and it's not cost effective. It's not a good deal in terms of the energy put in and the energy benefits that you get out, okay? Also, at those temperatures, matter becomes plasma, and it becomes really hard to contain it And you have to use magnetic fields to contain the plasma. It becomes very expensive and very complicated in order to actually contain that plasma on a commercial level to create nuclear energy in this manner. Now, how much energy is released in nuclear fusion? Again, the fusion of the two isotopes forms helium and a neutron. Energy is released because the total mass of the final nuclei is less than the total mass of the initial nuclei, okay? So we can compute the mass defect from this table, okay? These are just numbers that you just calculate. You can calculate these. The mass defect is 0.0189 atomic mass units, which means that the energy release is about 17.6 mega electron volts. Per nucleon, it's about 3.5, okay? For fission, it was about 0.9. So fusion would give us more energy per nucleon, but as I said before, you have to put so much energy in to heat the substances, and then you'd have to contain the plasma that it just doesn't. It's just not cost effective. It doesn't make sense to do that. Okay. And again, as I mentioned, stars are natural nuclear fusion reactors. So a couple of things, we'll study this when we talk about astrophysics. The density of interstellar space is not a vacuum, okay? There's about one hydrogen atom per cubic centimeter equivalent, okay? So what those atoms that make up, God, that's actually kind of a lot, huh? One atom per cubic centimeter. Anyway, it's mostly hydrogen and some helium, okay? When those atoms are compressed, then a star can form. But something needs to actually start the compression, okay? This can be exploding supernova, cosmic collision, something that will fuse those atoms together. So once it's started, it will continue naturally because the gravitational forces of the particles pull other particles in together, and as they're pulled together, they gain kinetic energy, the temperature goes up, and there becomes what's called a radiation pressure, which counters the force of gravity, which is what gives a star its spherical shape and its diameter. As they get closer together, the force of gravity increases, so the gas continues to collapse and gets hotter at an ever-increasing rate. Inside gets so hot, plasma is created and nuclear fusion takes place, okay? And it's this increase in mass during fusion that gives off energy as heat and light, gives off those photons that we talked about in that previous reaction, okay? A very common reaction inside of a star is 4 helium atoms, okay? Producing a gamma ray, a neutrino, and 2 electrons and a helium atom, okay? So remember that the universe is mostly made up of helium and hydrogen, okay? All atoms in the universe were made inside of stars, okay? And remember that we can tell by spectral analysis what kinds of elements are being created inside stars, or certainly in the atmospheres of stars, by examining these analyses, okay? And to finish this video, there's an example, okay? I want you to actually calculate the energy released in this reaction that we talked about in the last slide. Go ahead and pause the video and try this one. Okay. I got that the energy released is 24.7 mega electron volts. Okay, so that rounds out the video set, the 3 videos for 7.2. Next up, we're going to have some videos for topic 7.3, which is particle physics, which will lead us into our discussion of quantum mechanics.